I'm super pleased to introduce Robert H., actually Dr. Robert H. I've known Robert for quite a few years now, and sort of in two ways. One, I met him at the WISC conference years ago.
Yeah.
He did some tangible user interface work, which I was super impressed with. And then recently, of course, when Ayla just joined Autodesk, and eventually Robert joined Autodesk too. And little did I know that he was that guy from the conference that did that really super cool work, but was also known as Mr. Generative Components in the field of architecture. And it's pretty much who founded the Smart Geometry Conference.
Yeah.
Has sort of worked at some incredible places over the year and tons of experience in this area. And he's been working on this wonderful project called DesignScript for the past couple of years, which is I think a really wonderful piece of work, and I'm super happy that Autodesk is supporting this type of stuff that is really going to advance the state of the art of this stuff. And so without further ado, I'll introduce my friend Robert.
Okay.
Talk a little bit about DesignScript.
Thank you very much, Scott. Yeah. Okay, so I'd actually forgotten that we had met at that, I think it was 2001, wasn't it? In Raleigh or somewhere like that.
Yeah, it was an East Coast thing.
Yeah. So that's another chapter, the tangible user interface stuff. Anyway, so Gord said that, mentioned generative components. So I don't know if you've been watching over the summer the London Olympics, but the velodrome, the bicycle track, I should have put a slide in actually, was designed with generative components. And it was one of 60 entries into an architectural competition. So that's a really... It takes a long time to develop a piece of software and put it in the hands of the users and get a competition won and a building built. So maybe we should be aiming at a future Olympic stadium. I think I got a couple of slides in. Okay, so to start off with, let's just give a review of what we've done. We started off with, I don't know if you saw this demo, but this was like a tree under a roof, and you could move the tree around and the roof responded. We showed that in 2009. Then in 2010, we remodeled the roof of the Centre Pompidou in Metz using ASM solid modeling. This is a very complex surface with essentially holes drilled in it, boundaries imposed on it. And then these beams are defined by curves, which are in turn defined by planes that intersect that surface. But the interesting thing about the beams is that so that the curve is planar, but the beam runs along that curve, but twists to be normal to the surface. So to do that, we built a special kind of coordinate system whose x direction was tangent to the curve, and whose z direction was normal to the point on the surface. And then this building's been built. We were just doing a retrospective study, and the actual timbers were as glue laminated timber, but it had to be machined. These twisted beams had to be machined out of much larger pieces of wood. And of course, it's quite interesting. It's a very difficult design to justify, because it's meant to be based on the idea of a Chinese bamboo hat, which is essentially a very malleable material, and you actually twist the material. But when you scale something up, you have to machine it out of the solid, and everything goes wrong. So you should be actually using geodesic curves, which would be the natural curve of the wood on the surface. So I think that illustrates in sort of microcosm how an architect has an idea, and he scales it up completely outside the proper limit of the material, and so you end up with a manufacturing process which is completely suboptimal. Anyway, that's a distraction there. And then last year I'm going to show you this project. We integrated in Robot and SmartForm, which is a form finding software from our colleagues in the Engineering Practice Bureau Happold and Ecotect, and we built this little model, and we'll show that. And then this year, we've just given a paper at the Advances in Architectural Geometry conference in Paris, where we showed non-manifold, we showed the much more extensive DesignScript language and our IDE, which I'm going to show, and non-manifold topology linked to Green Building Studio. So I think that if you look at those kind of 4 slides, I think you can see that not only are we developing a language and the sort of computational infrastructure behind that language, but in order to show it to a user who is an architect or a designer, you have to include lots of other things. You have to include good geometry, links to analysis. So it becomes a sort of complete package. And of course, we'll get the tipping point is for a user, I see all this nice work. Is it sufficient for me to use to do the next competition entry for the next Olympic stadium? Yes or no? I can't just have a language. Thank you very much. It's got to be something that I can use. Okay, so essentially, I kind of step back from a little bit and say, okay, the architect or the engineer is designing a building. We are designing software, but more importantly, we are designing a learning curve, basically. And so this is a sequence of slides that I've shown previously, but essentially it's about effort and reward. How much effort do I have to put in for how much reward do I get back? And so with direct manipulation modeling, immediately you start doing something, you have some, for a little bit of effort, you get quite a lot of result. But actually, to change that, to modify that, to refine that model often takes a lot more energy. You've got to, if you've built some sequence of modeling, and then you suddenly say, yeah, but the setting out points that I used are wrong. Well, I'm terribly sorry. If you change the setting out points, nothing else is going to change. So you end up having to delete half the model and remodeling it. So though it's got lots of intuition and lots of gives you a good initial experience, actually to deal with a realistic design problem, it becomes very inefficient. So the next approach is to think about associative and parametric modeling. Here, to get for the same amount of effort you put in to begin with, you don't get very satisfactory results. You have to invest quite a lot in the parametric model. But once you've built the parametric model, then when you change the setting out points, everything's going to ripple through. And so you quickly get to a point where you overtake the user who's just doing direct manipulation. It becomes far more efficient. But you have to have the skill to define the parametric model. And with programming or scripting, you have to put a lot more effort in. And then you end up, though, with a much more powerful tool, which will overtake and do things that you couldn't do with parametric modeling. So our kind of hypothesis is, how can we combine all these different ways of working into a composite learning curve so that the user can start off with direct manipulation, he can then progress to parametric modeling, he can then progress to scripting. And the overall strategy here is that when the user is doing his direct manipulation, actually we're recording that under the hood for him, so that when he says, gosh, this modeling is getting a bit difficult, I'd like to switch to associative modeling. Yeah, we've already captured all those relationships. So he can start with direct manipulation, transition, this is what the 2 circles are, transition into a parametric modeling. And then when the parametric modeling gets too complicated and he wants to put in logic, like conditionals, for example, which are difficult, or iterations, which are very difficult to represent in an associative parametric system, then we can sort of peel back the graph, so to speak, and there is the code for him to directly operate on in a scripted form. So that's our kind of overall strategy. Of course, we are working backwards, which is rather sort of counterintuitive. In order to be able to peel back the graph and see the code, we have to have the code there in the first place. And so we're starting at the top right, whereas the user is going to be starting from the bottom left. So initially, our system is really more for an experienced user. Okay, so out of that set of slides, we get one dimension, which is there's going to be a range of skills, okay, and that's going to, from a scripting perspective, that's going to span from no programming skills through novice, proficient, and expert. Okay, but there's another dimension here, which is the range of modeling. Okay, you might be dealing with a very simple sketch, but if you're doing an Olympic stadium, which is going to seat 80,000 people, then there's going to be at least 80,000 components. Even if you just count the seats. So we've got to scale our system to suit the kinds of model complexity that our users are interested in. And then there's another third dimension, which is to span the range of design and engineering disciplines. And the reason we want to do that is that we want to provide an environment where different disciplines can work together, can collaborate, and indeed do kind of design optimization. So there's another kind of subtext here, which is we're trying to move away from vertical discipline-specific applications. Here's I'm a structural engineer, and this is a structural engineering package, and I'm an energy engineer, so here's my energy package, and I'm an architect, I'm interested in the kind of space planning. No. All those, to get an optimum building, all those three different systems have to come together because there are going to be trade-offs between them. So you'll see how we've done that by essentially having a sort of plug-in strategy. So we've got plugins for robot and smart form, and performative design, which is Andrew Marsh's new version of Ecotect, energy analysis for Green Building Studio. And how we see that is that we can effectively generate a solution space of different alternatives, and we'll do that in the cloud, so that each, instead of waiting for every solution to be computed on your computer, once you set it up, then you'll say, please give me a range of designs for different column spacing, different floor-to-floor heights, different overhangs, different facade treatments, and they will all be computed in the time it took to compute one solution because we were using cloud infrastructure. So that's the kind of broader context. Okay, so now focusing on DesignScript as a language, essentially what we're doing is comparing it with a general purpose language which has general functionality. So essentially DesignScript is a domain specific language. So in a domain specific language, we remove some of the generality that we think is beyond the needs of our domain user, but we add in specific domain concepts and we promote those to be first-class features of the language. And I think you'll see as you go through the presentation that the domain-specific items that we've added in are this concept of dependency, which is not around in regular programming languages, and also the way we treat collections. So buildings are made up of collections, and these collections vary in size and dimension. And also, there's another characteristics of the collections, which are that sometimes they can be produced by a single process, like, clad all these columns with this kind of rendering, okay? So that's an operation we want to apply to a particular collection. But hang on a second, there's one in the corner which is slightly different because that's exposed in this way. So we have collections and we have anomalies within those collections. So we've tried to provide those kind of collection operations as very convenient and first-class features of the language. Okay, so then the next thing we want to do is to think about our users as end-user programmers, or indeed as novice end-user programmers. And so again, we're going to remove some of the restrictions that are in some of the programming languages, particularly to make the language optionally typed, and specifically to blur the distinction between a single value of a particular type and a collection of the same type. So in C++ or C#, you can't pass a double and then an array of doubles. Oh, hang on a second, the array of doubles is a different type. So we want to, but that doesn't work for a user. Well, I've got one column and then I want to make an array of columns. So they're still columns, aren't they? So those kind of distinctions, which may be derived from object-oriented programming concepts, are there to help the compiler work out what the user's trying to do. But we're in a slightly different situation. We don't want to impose those restrictions. We're very conscious of, well, what are the concepts that the user has to learn before he can effectively use the language? And if we throw too many restrictions, too many concepts in, we're putting up a kind of abstraction barrier. And then the third thing we want to do is to integrate different kinds of programming concepts into the same language. So we know we've got imperative and associative, possibly declarative. So we want to make quite sure that we can handle multiple programming paradigms in DesignScript. So essentially, what's happened is that in the world of design computation, there are essentially two programming conventions. There's the imperative programming convention through Python and C# and Java, where the flow control is defined by for loops and if statements. They're explicit flow control statements, and if there's no flow control, we just drop through to the next statement. And if you go and take a programming course at a university, they're going to teach you these kind of languages. I'm quite sure you're all familiar with that. Okay, so the problem is that imperative may not be suitable for entry-level novice user. And certainly the environments, like I think this is Eclipse, is not sort of really very inviting. There's a lot of stuff to learn about here. The other programming tradition is the associative programming tradition, of which sort of generative components and Rhino Grasshopper are examples, where the user is defining flow control by linking together different nodes, so that the output of one node is used as the input for another node, or essentially writing a statement. The references that you would put on the right-hand side of that statement are being used to control the value of the variable that you're putting on the left-hand side of the statement. And this is really good for entry-level programming. I think that, looking at generative components and Rhino Grasshopper, I think the general conclusion is a lot of people who wouldn't have got into programming have been able to express their design logic using these tools. And that's a very beneficial effect that everybody's got to recognize. Okay, the problem is that it doesn't really scale to complex projects and to more accomplished users. So as soon as you get to sort of 50 nodes, the actual management of the graph starts to impose on the user. And I don't know what your thoughts are, but the feeling I get is that as the problem gets more complicated, the graph representation gets sort of exponentially more complicated, and its utility as an end-user programming device is reduced. And you could look at that and say, well, yeah, you've kind of spread things out, but actually, these 25 nodes could be reduced to a couple of lines of code. But how can I do that? Do I start nesting that into a group? It gets, and then how do I know? I've collapsed certain subgraphs into nodes, but how do I review that? I've got to start looking in depth in here. So there's a whole lot of extra tasks that you're asking the user to do, which is nothing about, I want to build this stadium. Why am I working out where the graph nodes are? And another factor is that it's very difficult to integrate these kind of systems with direct manipulation. So that's our kind of motivation in DesignScript, is to combine some familiar concepts of imperative programming with some more original concepts in associative programming. I think the associative programming is there in the graph node diagram systems, but what has happened is that the designers of these systems have focused so much on the graph node that they haven't really bothered to think about the underlying representation. So in another kind of slide, I've got a sort of comparison. If I was, if the user wanted to draw 2 points in a line, how many lines of code would that represent in DesignScript, in generative components, and in Rhino Grasshopper? So in DesignScript, it'd be like a couple of lines. In generative components, it's about 25 lines. It's a sort of name value pair data format. in Rhino Grasshopper, it's about 250 lines. It's this enormous XML file. And so the problem is that as the user sort of goes up the scale, he can't go from his graph model to see what the underlying logic is. I mean, one of the experience I had in the smart geometry group and with generative components is that after a while, people said, okay, thank you very much for this graph, but actually, I'll just go and edit the file. Well, at least with 25 lines, you have a chance at editing it. But 250 lines, you get one kind of part of you don't balance your XML. You're lost. What went wrong? So there is a kind of what we're trying to do is to make quite sure that when the user peels back the graph, there's something really understandable and efficient underneath. So I now want to describe, so we've introduced this idea of different programming paradigms, and I just want to sort of compare this with a numeric and a geometric example, because I think what my purpose of this is to show you that each programming paradigm works well for different kinds of data. So if I had the following statement, A equals 2, B equals 2 times A equals 5, okay, then if that's an imperative program, you'd say, well, that's absolutely fine. I've changed the value of A. I don't expect B to update. If I wanted B to update, I would put that in my program. But if we look at a simple sort of geometric example, I draw a curve, okay, and I project a point. B is a point, is A projected onto my curve. Then I go and move A. I would expect the point on the curve to move, but it doesn't, because until I actually say go and update the second line, or repeat the second line as the fourth line, nothing's going to happen. Well, that's pretty bad. If you go to a CAD system and you draw a construction and you go back and move something, you expect the thing to move. Okay, so that's what we can do with associative programming. But when we look at it at a sort of numeric level, okay, A equals 2, B equals 2 times A equals 5, suddenly B changes, okay, and you'll see the kind of execution pointer go back. Well, that's a bit sort of counterintuitive if I've been learning imperative programming. But it's exactly what you want in a graphical situation. Yeah, I moved A and B updated. Well, that's what I expect. So here we're showing kind of the redefinition of A. But what we also want to do is to show some incremental change. I'm not just like redefining the position of A. I'm actually saying, nudge it in a particular direction. And so the translate will be equivalent to a move command. Oh yes, I've computed the position of A, and now I just want to take my cursor and drag it a little bit. Okay. So this is having this modifier where A equals A dot translate. So A is on the right-hand side. That is the previous state of A, actually enables, although we haven't actually implemented this, the programming language has the kind of infrastructure to accept direct manipulations to actually capture what the user does. So there's a kind of, I've got, you can download this from the lab site, a kind of description of DesignScript. And here's our kind of, we're going to show the IDE, and I hope I can. Okay, so I've written a little program while I was waiting. Okay, if I can get hold of this thing. Okay, which is pretty simple. So I'm going to run this in debug. Okay, so I'm starting off and I'm going to create a point. Okay, there's the point, and this point is created with 0.5, 0.5, 0.5 with where each coordinate is a single value. Okay, so I can now replace a single value with a range expression, go from 5 to 10 in steps of 1. Okay, and now I get a row of 5 points. So this is an aspect of DesignScript where we blur the distinction between a single value and a collection. So anywhere where you can put a single value in, you can put a collection in, and we've got we'll see a range of these different conventions here. So now I'm going to, in the next one, I'm going to, as we single step, we actually create the geometry and then remove the old geometry. So now I've got a range, in line 6, I've got a range for x and y. So for every value of x, I get I select a different value for y. So that's equivalent to a zipped collection in Python, basically. Okay, so now we're introducing, in the next line, line 7, okay, we're introducing this idea of a replication guide, which is saying this is effectively collapsing a double for loop, a nested for loop. Okay, so the outer loop is going to be for x. That's what the 1 stands for. And 2 is the inner loop. So we can have a sequence of for loops. Okay, so now when I do that, for every value of x, I'm getting every value of y. So now I can, now start has gone from being a singleton to a one-dimensional collection. This is a one-dimensional collection, although it's got 2 input one-dimensional collections. Because it's a zipped collection, it's going to be one-dimensional. Now start is a 2-dimensional collection of x and y. So now with a 2-dimensional collection, I can drop that straight into a B-spline curve by vertices. Okay, so now if I go back in line 11 and I switch around the replication guides from 1 to 2 to 2 to 1, okay, I'm going to do that, and then you'll see the execution pointer goes back and say, oh, hang on a second, you've changed start, so I now need to so now I've just flipped round and I'm sampling that array of points in a different direction. Okay, so then we've extended the concept of a range expression so that we can have, like, from start to end in a defined increment, to be from start to end with an approximate increment. This is the tilde expression. Okay, and what this does is solve what I would call the staircase problem. Okay, so in a staircase, you say, okay, here's my floor-to-floor height. I want my riser to be approximately 8 inches or whatever centimeters that is. Okay, but it may not be exactly 8 inches. But whatever it is, it's got to be near enough 8 inches, and it's got to be uniformly distributed. So if I change my floor-to-floor height, I'll gradually, every riser will increase until, whoops, suddenly we go over that limit, and we'll get like one more riser, but they'll all be slightly short. Okay, so that the tilde like gives the user direct access to that, and then the hash is just says give me divide this range in by 2, basically. So and you can see the execution cursor popping back to line 9 to update it. Okay, so now I think I'm putting it back to its original form. So I've now got that. And then I'm going to define an endpoint, which is some place up there. You can see it, okay? Oops. And then I'm going to come down here, and I'm going to say, okay, now I want to join, I can index into the array, the start array, and create a line. And then depending on my indexing, I will create an array, and then I can do the whole collection. And then I can do negative indexing to just select the last one, the last row, or the last member. And then I can define a variable for the indexing and use that. And then I can make index as a collection. and it seems to be trapped there. Okay, so that just gives you an idea of some of the features of the associative language and how the IDE works. And let me just give you, a typical kind of model that we've tried to emulate. This is the roof of the Smithsonian. It's the extension to the National Gallery of Art on the Mall in Washington by Foster and Partners. So, I just produced a kind of a look-alike here roof, which is effectively is a series of sine waves. We'll see that there's a front-to-back sine wave and a lateral sine wave and then a high-frequency sine wave, and they're all added together to give this kind of beautiful effect, which I think would be very difficult to draw by hand. And then we can tube it up, and then we can change the number of cycles, for example, and then we can even drape it over a surface, and I've just offset it from the surface, so as the surface changes. So this is the kind of thing that we can do. So coming on to the different plugins that we've built, we're going to look at 3 plugins: associative, imperative, or 2 language facilities, smart form from Bureau Happold, robot structural analysis, and performative design by Andrew Marsh. So our sample building, this was part of the paper that we gave at the Design Modeling Symposium in Berlin last October, 12 months ago. Essentially, there's a sort of ruined art gallery at the back of the University of the Arts. So we wanted to sort of imagine modeling a roof over this space. So we first of all just make the context model, and then we put down an array of points, and then using the smartphone we kind of wire them all up with bars, and then we can relax this shape to form this form, and then changing the slack length of different members, we can actually kind of craft a shape onto the roof. And then we can take that node and bar information into Robot and get all the members sized. And then coming back into DesignScript, we can color code the members red to green of whether they are over or underutilized. And then each little quadrilateral can be the basis for a little shading device, a little kind of half pyramidal shading device, and you can see a kind of notional sun angle out there. So if we change the sun around, we could imagine that these shading devices are moving with the sun. And then on the surface of the shading devices, we can calculate the insulation using Ecotect, or now this performative design tool. And so essentially, if the user changes the criteria for form finding, that's going to ripple through. It's going to redo the structural analysis, resize the members, redefine the shading devices, and recompute the insulation. And so this would be an environment in which an architect and a building services engineer, structural engineer could all kind of collaborate. And we've got DesignScript classes which are calling into the respective DLLs. We're just repackaging existing functionality. Including just changing the spacing of the points. So that was the kind of 14 different processes that we went through there. So the next one example is where we're using solid modeling and non-manifold modeling and energy analysis. So this part is based on the paper that we gave at the Architectural Geometry Conference in Paris a month ago. And here we're harnessing some facilities in the Autodesk Shape Manager, the solid modeling tools that are built in Cambridge and Novi. Okay, so we want to make a distinction between, so this is quite an innovative use of solid modeling. Conventionally, solid modeling is used for making a mechanical part where the boundary is between the outside void and the inside material. Okay, so that's a manifold solid. A non-manifold solid has internal partitions, internal faces. And a non-manifold solid is created using what is called non-regular modeling operations. So in this example, I've taken two cubes and I've unioned. I've done a non-regular union. If it had been a regular union, that red cell in the middle wouldn't exist. It would just be one continuous boundary. But instead, I've intersected the two cubes and looked at the total set of intersecting faces. In particular, I've looked at this red cell, which is the intersect cell. And then I've chosen one of those faces and used the defining geometry of that face to construct this yellow wall object. So here I'm using solid modeling in two different ways. One to do a spatial modeling of a building, and then another one to actually populate that spatial model with a material model. So a lot of the work done in architectural geometry has been about facades of buildings. And very few people have actually looked at buildings from a point of view of spatial enclosure and organization. So the model on the right is a slightly fictitious one, but it's not the hotel I stayed in last night, but it might have been. Okay, but I've taken a block and I've sliced it into floors and vertically into walls. And then I've taken this kind of inverted cone and I just like dropped it on the building, and that's the atrium. You know, no, I mean, I'm not going to succeed in Architecture 101 at Waterloo University, but my purpose is to demonstrate the logic of these modeling capabilities, not my particular use of them. So this contrasts with building a conventional BIM model, where we're just arranging physical components together, and then retrospectively we've got to go and analyze the spatial arrangement. Okay, so here's our set of Boolean operations that most probably everybody is familiar with. Okay, so if I have a regular union, for example, all the aspects of B in A and A in B are removed. Okay, I think that's, and if I slice, the last column, if I slice an object with a plane, I will get two resulting objects. Okay, in non-regular operations, if I keep all the faces of B in A and A in B in the non-regular union, in the impose, I have a sort of a halfway house. I keep one set of faces but remove the other set of faces. I was using the impose on that atrium model. So there's the example of the non-manifold union, and here's an example of an impose operation. And so we've essentially taken, as continuing our theme of domain-specific end-user programming, we've taken the very complex topological data structures out of ASM and exposed their logic in a way which we feel is accessible to an architect. So we're exposing the outer shell of a solid, the internal cells, the faces, the edges, and the vertices. So if you look at this, I don't know if it's readable, but you know, a cell has got adjacent cells and it's got cell faces, and cell face and you know, a cell face has its associated cells. So effectively, you can sort of arrive in one space, one cell, and you can query all the faces, all the walls, and say, well, what's the cell on the other side of you? Oh, and now I move to that cell. So we can actually walk the whole model. Okay, that's the different descriptions of the different topological classes. Illustrating this, if I start off with a block which represents my building, I might want to make that building more interesting, so I define a surface. I subtract or trim the solid with the surface. Okay, well, that's perfectly normal stuff. I can extract the edges. This is a manifold solid. I can extract the edges, and I can populate those edges with an extrusion, for example, representing the structure. Okay, but that's not so interesting. what I can do, which is more realistic, is to say, okay, I'll define some planes to split this solid into its constituent cells. Okay, now I can populate those edges. I'm just actually, I built a sort of structure component that I just took the whole collection of edges out of this non-manifold solid and threw it at this class. Okay, and it worked out from how many faces which were defining the edge, where that edge was. Was it in the middle of the solid, or on the face of the solid, or on the corner of the solid? And then I could approximately find out whether it was vertical or horizontal. And so I could actually automatically populate my structural model using this rule-based system. So then what I did was to create an atrium, not a very kind of beautiful atrium, but then in sort of amoeba fashion, I got the building to kind of swallow the atrium. And as the atrium progresses through the building, so you can see that edges are being created and other edges are disappearing until it sort of comes out the other side and it's all forgotten about. Okay, so you can imagine that in this kind of modeling, we don't actually, if we go, let me go back a second. We don't say, oh, I see that edge. I think I'll populate it with that kind of beam because, that edge is going to disappear. What's going to happen to that beam? So unless you had that combination of scripting and modeling, you would be lost. If you made any modification to the kind of a flat model, it would not respond in an intelligent way. And so not only can we use this technique for like a structural model, but we can use it for the actual volumetric, the cell model. So I can just expand it up a bit, do another explosion. So you can see all these different cells forming. So this is rather a kind of idealized representation of a building. So we can now attribute this. The cells can have, obviously have their volume, but they can be defined with their desired internal conditions, occupancy rate, air change, for example, additional loads. And then the faces can represent they have an area, and they can be given thermal properties. Now, we don't actually have to model the thickness of the wall. We just have this logical representation of an attributed zero thickness face. And then we can pass this, we've written a plugin that generates Green Building Studio information. So imagine, here's my original building, here's my set of planes. Of course, that set of planes could be defined by a range expression. I could be moving them up and down. I could have different floor-to-floor heights on the ground floor. I might have a mixed-use building with retail and a hotel and offices and apartments. Then I can slice that up, and then I can Green Building Studio only deals with faceted or planar information, so I can pass that through. I can create a subdivision mesh from the topological model. That can go into, I can define what kind of building it is, what kind of use. That generates the Green Building XML format, and then we go off to the server, and then back comes the CO2 emissions and the annual energy consumption, which we can then put back into a dashboard to present to the user. So that's an example where we've taken DesignScript and, if you like, done a little bit of the end-to-end processing. It's not just the language, it's representing the building in a light way, where the lightness and the ease of modeling is better driven by a scripting approach, and then we've demonstrated it by actually saying, well, here's some real engineering analysis and simulation that an architect would be interested in. Again, the combining the familiar and the novel concept. So I'm not going to kind of do this in real time in front of you, but this is just a little domey roof that I built, I want to show you different ways of combining imperative and associative programming. So in the if I was writing Python, I would have all these for loops. I'm creating my points in X and Y, and then I'm defining some sine waves to give it some height, and then I've got the columns in the corner. And it's a kind of it's quite a long program, but it doesn't stretch the imagination. But if I write the same intent in an associative programming, I get a really compact code. And just looking at the example here, just pulling out the x and y, I've got two sine waves, so I'm just passing in 0 to 180 for the increments that I want for the column spacing times the x height is giving me the kind of side-to-side sine wave, then the y array is giving me the front-to-back, and then to get the height, I'm just adding the two one-dimensional arrays together, but doing with replication guides, I'll end up with a two-dimensional array of heights, and then I just use that to create my sort of domey roof. So now we're looking at how can we combine scripting and interaction. So one way we can do that is to put down sliders. So you can click on a literal value, up comes a slider, and then we can play with that, go to another variable. So we're trying to, rather than putting programming in the model, we're putting interaction into the program. And so now, having built that, we've got this very compact associative code. What we're going to do now is to sort of tab it across a bit and put an imperative while loop around it, where it's a sort of like symbolic, if you like, optimizer. So we're going to say, okay, we're going to put a breakpoint at this increase in height, and we've defined the volume. We're going to measure the volume of all the tubes, and the while loop is, while the volume is less than 10, increment the height. So what we want to do is to pump this thing up until we get to a particular condition where we want to stop. We're not quite, we can't drive it to that condition. We've actually got to iterate to that. So here we have an associative model being controlled by an outer kind of searching, hill climbing sort of process. So now I put a breakpoint at height. I drag some of the variables into the watch window so I can see both x height and volume, and now I can click next on my in debug mode, and the thing pumps up until it gets to the final value, and then it stops. So as a sort of template or pattern, please, somebody who is a better architect than I am, design a better building and put it in a more realistic optimization loop. But this is like a template that you could use. So in summary, I think we've got a number of different eras. We've had the 2D drafting era, which was the initial kind of, in quotes, democratization of technology. Okay, we can create an application like AutoCAD, which emulates what you would have done on a drawing board. Okay, but you still got a collection of distinct drawings. You're still distributing your design over multiple independent, uncoordinated representations. Yes, you have the advantage of being able to retrofit that to existing drawing production processes, but there's been no engagement with the creative mind of the architect with the idea of computation. So in the kind of BIM era, okay, instead of literally drawing all the drawings, no, we step back from that and we define a single building model, and from that we extract drawings and other schedules and other reports. But I don't know if you've ever watched anybody using, a BIM tool. There's a tremendous amount of manual effort. Oh, I'm moving this wall here. Oh, I'm putting this window in this wall. It's totally exhausting. It doesn't scale. It doesn't, if I want to change the floor-to-floor height or put a kind of slope in the facade, I've got to go and modify all those individual components. A lot of handcrafting. As the BIM era extended, we could link it to analytical models for simulation. But again, as I kind of showed in the earlier part of the presentation, building an architectural model out of components is not necessarily the right way to drive your analytical tools, nor is it the right way to think about the building. You're saying to the architect, before you think about the concept of your building, you've got to define what your components are. And the architect's saying, no, the components come second. Why are you forcing me to do this out of sequence? So that's where, if you like, the design computation era comes in. We are creating tools that enable you to define the generative process. And now the building model is more the generated data. So we've now got generative data, generated data, and derived data. And then, of course, reality. And, of course, in that reality, we're still only, we're still cutting, plotting a set of drawings and walking on to a building site with a rolled up set of drawings. Okay, so, there's an opportunity here, I think, in the second phase of the kind of design computation era, where not only, as we've shown in this presentation, we can directly link the analytical models and simulation models directly to DesignScript and get more feedback early in the design process from a lighter representation. But we can directly take that representation into fabrication. This is using a term, geometric normalization, that Fabian Schurer from Design Production uses, which is said, I could represent the outer shape of everything and get, but actually all I want is that tool cutter path, please, and the vector where the hole is going to be drilled. That's all I actually need. So, normalize, if you like, normalization is something that already happened here. This is, BIM is the application of three-dimensional geometry and hidden line removal with code normalization rules, which basically say, if you're going to define something, only define it once. Okay, this is geometric normalization, which says, and if you're going to define it once, define it in the minimum form. And now we can go and directly create our building either through digital fabrication or robotic construction. So I hope in this presentation that I've actually sort of not only talked about DesignScript as a language, but shown you how it fits into the present context and potentially future context of how the user that we're directed at, which is an architect and building engineer, how he would use that with geometry and topology and analysis and simulation tools. So, thank you. Questions? Philip.
Thank you very much for allowing me to visit this way. It's a real privilege.
Should you introduce yourself?
I'm sorry. I'm Philip Beasley, and I'm teaching at Waterloo, and I'm very happy that we are with Autodesk Research are going to be entering into some collaboration in the next year or so on the subject of responsive and near living architecture. I'm undertaking the work with colleagues. A question would be to ask you to dwell a bit more on the while state that came fairly late in your presentation, because that seems to have such an incredibly potent quality in terms of opening the question of optimization, but also of learning of functions and adaptation. Would you mind just dwelling on that condition?
Yeah, I did dwell on it. And if the while loop fails, which it did do, that loop's going to go on forever. So the first time, it's a lot of these tools are not for the unwary to use. If your limit, you've got to be very careful that limit condition will be reached. It's like, if you have a recursion, you don't have a limit condition, you will just go on. But yes, I think that's, so you might want to put like a safety net in, have some counter. If it gets to 1,000 and it hasn't converged, you stop. Yes, I think a language is such an interesting idea because it opens up the possibility for different people to plug their own logic in and to combine these tools in essentially unforeseen ways, I think. And I think that's the ultimate accolade, if you like, is when people take your tools and use them in ways that the original designers did not anticipate. That demonstrates that the tools are really extensible, that you've set up something which goes beyond your own horizons. So, the while statement is a logical statement. It's usually fed by some variable that is changing by the action of the statements within the kind of the curly braces within the block that is being controlled by the while. And so it's a feedback. It's really a feedback mechanism. And that's been, I think, really an important innovation, because we want, in the associative modeling, that's really there to capture somebody's, to do design capture. The user can just draw something, okay, and that can be captured as the associative script. So how do you combine intuitive drawing and sketching and modeling with the concept of optimization, where you might have different, either the same person has this capability to span these different ways of thinking, or you have a design team where there are specialists who are collaborating together. And one is saying, oh, I've got this idea for this beautiful building, and the other person is saying, yes, but it shouldn't be greater than this or less than that. How can we take your idea and find out how that idea, what that idea is like when it reaches this limit, in a way that avoids having just to manually repeated redrawing this. I want to get away from the over dependence on the mechanical effort of drawing, but I don't want to exclude it. I want to capture it and harness it. So direct manipulation is not. Some people think, oh, scripting is over here, and direct manipulation and more intuitive operations are over here, and they don't actually intersect. Because if I in a conventional system, if I scripted something and then I modified it, okay, and then I ran the script again, I'd lose my modifications. Or I have no way, I define the radius of this circle and built a whole lot of stuff. In an interactive system, I can change the radius of the circle, but I can't change what depends on that circle. So here we're looking at interaction in terms of, yes, when I change the radius of the circle, the whole rest of the model will update. So I'm combining both rule-based approaches to design and interactive approaches to design, which is, I'm not quite sure what the rules are, but if you give me the tool, I'll manipulate it and I'll tell you when I've got something nice. How do we combine those two? That's the challenge. But whatever we do, unlike other design systems where we just record the data, oh, you moved this thing to these particular coordinates. No. We want to record what the user does, even when he's in his intuitive mode, as a script, so that he can go back and review that script. Oh, so this is what I did. Okay, now I could embellish that. I could embellish what I did by doing some more, squish and squash, or I could embellish it by putting another while loop in. Okay, now those are two ways of thinking. How can we combine these different ways of thinking in one tool? And I mean, just think of the challenges you could throw at your unsuspecting students, Philip.
Hey, Robert, I really loved your first slides where you're showing about sort of building these types of learning curves.
Yeah.
It's just a brilliant way to present the work. It struck me that, maybe that's a fairly simplistic view of those learning curves. Like, I was thinking about sort of software development, where we get into this thing where we design these systems that are fairly flexible, but there is a limit to their expressibility, and there is a limit to their flexibility. And so you're sort of faced with the tact of, well, do I go really abstract in the beginning, and then I have to deal with having to deal with a very general system. So it's sort of it's hard to learn and it's hard to modify because it's so general, versus sort of focusing a bit more. And I'm wondering if you thought about how that plays off against, sort of that, well, we always start with a clean slate and you just build it manually sort of thing. There seems to be some trade-off where you decide, look, I'm going to narrow my range of solutions.
Yeah.
Yes, I think it's okay. I think a lot of so people who write computer design programs have a model of their user and his activities, and we've got this idea of conceptual design. And Philip can kind of jump in here if he thinks I'm getting this wrong. And the experience I've got is that software developers think of conceptual design as, oh, I drew this block and I rounded the corners. It's a sort of top-down idea. The architect always starts with what the building will look like. Okay, but in fact, I think that there's a sort of new form of design, which is like emergent design, which comes off, no, I want to use this kind of component or this kind of joint. I want to have these kind of relationships between the components. Let me see what shape emerges. Okay, so this is, it all depends who you listen to. If you go and do some user studies and you go to the existing practices, you'll find senior partners and, design associates who are out with the 4B pencil and the felt tip pen and they're sketching this top-down approach to design. But if you're a graduate from Waterloo or MIT or, SciArc or somewhere like that, it's very much, MTech at the AA, it's very much an emergent approach where we are interested in not just the components, but their behavior and their interaction and satisfying conditions, and that the form will emerge from that. So I think that latter kind of designer needs tools. He doesn't need the intuitive sketching tools. He needs tools to define the components and their component behavior, and to define the context within these kind of genotypes will grow and respond.
So maybe I'm sort of like I was trying to draw the analogy to general software development, where we don't sort of, well, maybe in the bad world we bottom up sort of thing, but that's building things out of the lower level components and sort of experimenting with them is not sort of the way we approach it. But it makes much more sense in your context because you're somewhere in that middle ground of abstraction where it starts to make sense.
Yeah, I think that
and you have fixed.
The idea that software development is top down. Like, I've got this algorithm and I'm going to implement it. I think that. Again, from practice or from education, it could be a remark. But I think the designer usually starts off with an exemplar. He says, "This is the kind of thing I want to do." Okay, now how do I generalize it? Okay, he doesn't start off with, "I've got an algorithm for doing something." So, my suspicion, and talking to other computer scientists, that actually, professional programmers often start off with generalizing an example rather than starting off with some abstraction. And maybe it depends on the algorithm. And so we want tools that allow for exploration, that very quickly I can do something, and I'm going to oh, this works. And also that's that feedback. Okay, I made some investment and I got rewarded for that investment. Okay, that will help me, persuade me to make a bigger investment. So I think it's very much programming and by trying to look at something and say, how would I describe that programmatically? Now I have to describe it. Okay, if I change this variable, does that now respond in the way? So you move from building an example to separating out what are the variables that are going to be the design drivers and what are the reporting variables which are going to be the performance indicators. So I don't know, I think it could be a very interesting area between us and a teacher of design computation, which is sort of software engineering for computational designers. Like, if I've got beyond the hacking stage, how do I make some method, some systematic method, where I don't just have all this pile of variables and lots of geometry coming out. I start to classify things into drivers and performance indicators and things which ways in which my program can control alternatives, and then searching for alternatives. So I think one of the advantages of design computation is that potentially it gives you logical tools to structure your design process. So it's not just, oh, the computer can help me draw a funny curve. There's logic in the programming system. And I would like, one of the kind of higher level objectives of something like DesignScript is to help move the user from this anything goes exploratory approach to programming and design to something which is very much more systematic. Because ultimately, if your building is built because this script ran, and something went wrong to your building, okay, you might end up in court with the lawyer from the other side saying, well, what was this script? Let me see it. So it can become serious business, and it should be structured in a way that does justice to your thoughts and explains them. So,
I wonder if I'll just chime in, Robert, since you kindly included me. If a preceding generation of architectural designers was really inspired by the kind of top-down, back-of-the-envelope sketch that's exemplified by SketchUp becoming a tool that really caught fire, and was arguably one of the most important transformative tools in the immediately preceding generation. And if a current generation has now, in a similar way, caught fire on Grasshopper, you might have to say, and the facility of scripting bottom up, becoming a popular term, which then produces, without knowing where you're going, a formidable amount of involvement and wonderful immediate effects. Oh, look what happens! I work with this, a beautiful kind of irresponsibility, a remarkable kind of effective playing, and that I'd suggest that's exemplified by the Media Lab. In the ethic of design playing, the model of the sandbox, let's say. Both of those, however, the extremism of the top-down model, exemplified by SketchUp, and also of the bottom-up, exemplified by Grasshopper, or perhaps Max MSP in parallel disciplines, which get jammed and clogged very, very quickly when you try to do serious things with them, and things grind to a halt and become an absolute nightmare of us because every single operation has to be done again and again and again. In contrast to those two extremes, bottom up and top down preceding it, I'll suggest that that we can now take for granted this next generation of designers understanding scripting as a fundament, and a new language emerging of quasi-periodic systems and intermediate states and layering, rather than the kind of very binary top-down and bottom-up language. And something like quasi-periodic, better words than that, will stuttering and fluxing and cycling and oscillating in a positive state will become languages. And that's why I'm very moved by the while states and the watch states, right, in parallel, with the offering of this kind of tool, which can really work with elegance and optimization, but at the same time works transparently enough that you can have your hands, in a pretty transparent dashboard on things as they go, so you can make jigs and tools and work with a component-based approach. I think it's a tremendously potent tool that you're offering that very directly matches the way the next generation will be working.
Yeah, well, I very much appreciate your comments. I think that what we've done here is to have some innovation, which is the associative language, but we've also if you like, respected the tradition of programming, like the kind of Visual Studio effect, which has the watch windows and the breakpoints, and and also the imperative programming. And essentially, last year in the Berlin workshop, we just had the associative language, and we got some very interesting results. But the thought was, well, I don't want to have to, if I've got something which is really better expressed in an imperative language, I don't want to have to force it into this translation to associative. And so we really took a leaf out of, if you like, the history of development of C++. So C++ combines imperative programming and object-oriented programming. And the preceding object-oriented programming language was Smalltalk, where everything had to be an object. If I want to add two numbers together, no, hang on a second, you haven't got a plus sign. You have to send a message to this number to add it to this other number over here. So sometimes innovation in computer languages is it's so kind of rigid. It's sort of like, this is a new paradigm, and you're going to use it for absolutely everything. And the next generation said, yeah, there was something good about that paradigm, but not universally. So it's far better to produce a hybrid language which combines existing imperative, in the case of C++, existing imperative programming ideas with object-oriented ideas where they were appropriate. And so I think we've kind of done a very similar thing. We said, look, we invented, if you like, this associative programming convention to be a more elegant abstraction of graph-based programming. Okay, but in itself, it's not complete. We will now combine it with imperative programming and with a simplified version of Visual Studio. So you don't get lost in the complexities, but you do have this idea of single-step debugging, of stepping in, stepping out of putting watch windows. And now we have, I think, a much more universal tool. So we're innovating in terms of adding the associative programming, and we're integrating. Another aspect of our innovation is to integrate this with existing programming conventions. And I think this could be quite interesting from a teaching perspective, because you could say to your students, well, okay, program this imperatively. Now reprogram it associatively. Now, which bits of your ideas are more naturally expressed in these different programming paradigms? How can we combine them? And of course, the little example I gave is putting the associative model inside the imperative while loop. But there's lots of, it's a completely universal language. If, for example, inside that associative model, if I had a collection, I could iterate over that collection using an imperative for loop. So you can embed any kind of language in any other kind of language. It's a completely universal approach. And I think that we are only ourselves, and we are only learning, we've still got to learn quite a lot about how to use these tools, So I'm quite sure that people in academia and in the research aspects of practice will have, some interesting, fun applying this language.
So maybe we should, I see people are leaving, we went over time. So thank Robert again, and